And so again, this is just showing you one example where you can see like you have again two classes, blue and purple, and in this case they are clearly separable, right? And in this case you can see this is the decision boundary and these are your support vectors. So this 0.1 and this 0.8 are actually crossing the support vector, but still they're not crossing like your decision boundary. Okay, so that's kind of an easy case. The second scenario here, you can see like they're crossing the support vectors, but again, some of the samples are actually crossing even the decision boundary. Okay, so in these samples, this is like just one sample solution you can have. So this will be like your decision boundary, and these will be your support vectors. And it's just showing that you will have allowable samples on the wrong side of your plane. Okay, so now let's try to understand like the effect of C, which is the parameter in your support vector machines, how that changes like the decision boundary, and how will that change the support vectors you will have. And again, this is like all four are corresponding to the same training data. And in the first, you have like a very large value of C, which means you are trying to allow like a lot of samples which can cross the boundary, which can cross the support vectors. So in that case, this is the decision boundary, which is kind of learned. And if you will look carefully, I mean, this looks fine, but again, there are a lot of like these blue dots right over here, which are kind of on the wrong side of the decision boundary. And if you pay attention to like these blue dots, none of these dots are actually on the right side of the support vector. All of are like in the wrong side. And same is the case with the purple ones. So it means like for this particular training data set, you need like a smaller value of C. You're actually allowing a lot of error. You're relaxing a lot. Okay. And this, again, these three are like as you try to reduce the budget C. And again, then you can see like your decision boundary is actually changing. It's kind of rotating as well. It's shifting. It's moving towards the purple side. And now some of the samples are actually on the right side of the support vectors. Some over here are also on the right side of the support vectors. Okay, so again, if you reduce it further, you will get something like this. And again, it's hard to say like which of these is correct. Of course, this is wrong. We can clearly see this is like the value of C is too high. But the other ones, again, this we can say like it's too high because most of these samples are within the margins. But between these two, it's hard to say like which one of these is better. And that's why we have like when you train your models or train your classifiers, you have three different splits. You have training split, you have validation split, and then you have testing split. So in this scenario, what you're going to do is you can actually set some value of C, and then you will evaluate that model on your validation set, and then you can just compare those two. And if like this C is actually better on validation, you will pick this. If this one is better, you will pick this. And whatever that model is, then you will use that model with the final selected C on the test set. So this is, I think, something interesting. And SVM, they do work, and like optimizing these parameters. If your data set is not too huge, it's pretty fast. And I myself has done this like a lot of time earlier when there were no neural networks. And what we used to do is we actually just used to do grid search. So we'll start from like a very high value of C and then keep incrementing it or keep decrementing it with small values. And then we'll kind of explore all the space and then just test all those models on the validation set. Okay, so that's called, you can say you're trying to like fine tune your parameters to determine like a better model on the target data set. Okay, and it is required because all data sets are different. And when I say all data sets are different, so, and there are a lot of different ways they can be different, but what we are interested in here is like this data set is like what we're interested in, what's the distribution of the samples like in this embedding space. Okay, so that's a unique property of this data set. And again, if you have a different data set like this scattered plot over here might look different. And that's why we need to hypertune or fine tune these parameters.